This video is about the superstructure, something I call a superstructure. It is a unified field theory based on a concept of inversions, of polarized inversions. We can see here we have the XY axis crossing, and at the intersection, the geometry becomes something that we don't fully understand. But what I'm going to attempt to explain is how reality is derived from this. On the right side of the screen is one-dimensional linear objects. This comes out on the left side. Okay, on the left side it's a one-dimensional linear objects. So bring it a little closer. So the idea is to get all that stuff that's on the left side to invert over to the right side so that we can have something called reality. But what happens from this is this. The X on the top right is on the outside of the line, whereas following the line down, it's still, let's get that over there, it's still on the same line, but it's on the inside of the inversion. So that's a 60-degree angle there where those two arrows are. That's 60 degrees, and it represents a 60-degree arc also. It represents a equilateral triangle. So from that we can understand that this exists within the inversion model. So this is an equilateral triangle, and what we're going to attempt to show here is that this being a full working model of the superstructure, we can see that there's prime numbers involved in here. The prime number I selected to use here, which would be the only one possible that could perform this function, is the 137 prime. 137 prime is unique to this because as the inversion goes, or as inversions go, we have the number 3 to begin with, because the superstructure represents the number 3. It represents 3 linear lines. It also represents the equilateral triangle, and it represents, here's the 3 one-dimensional lines that it represents. This is the superstructure, and each one-dimensional line is represented by 37 to equal the total numerically. Well, we have 111, so each line represents 37, the sum being 111. From this structure, we can build equilateral triangle, or we can build still 3 lines. That's 3 lines there. It's only 6 because of what we need it for. This is going to be a version of the superstructure that works inside a crystal. Now, here is the crystal model. Uprighted. Here is the crystal model, and if we look really close and bring this closer in and closer in, we can see at the crystal's lateral plane there, the cross-section of that profile of the crystal, we can see the superstructure. All 6, it's a hexagon. This is a 6-sided quartz crystal, and it's fitted right in there because this is what's actually happening inside a crystal. This is why we can produce the electricity that comes out of a crystal. And what we have by comparison Let me back this up a little bit so that we can get a good idea of what's going on here. With this crystal, by comparison, we can have, alright, there's the lateral plane of the crystal, whoop, that one right there, and we have the inversions going back and forth because of the polarization of the X and Y plane. Let's go back to the 6 sides, the internal crystal. There's the 3 dimensions. Now this superstructure takes the shape of different geometry because of its elusiveness. It's about as elusive as the 137 prime. So getting back to the full working model of the superstructure, we see that, get in the middle there, we see that as the composites are broken down to the primes, it equals out. This is the only prime that can do this. The 371 opposes the 173, the 731 opposes the 137, and so on and so forth. Each one being polar opposite. Composite, go down, prime, whoops, this way, composite, prime, composite, prime, composite, prime. So we have that fixed into the model, and the inversion, the inversion opposite is also 137, 731 is also a prime and a composite. So we have total polarization. This shows us that the 137 prime is ideal for this. And by the way, the structure is 6 equilateral triangles as hexagons go. 60 degrees is equal to that of the 260s making the 120 of polarization is equal to the 37 leg of the equilateral triangle. So from that we can go back to the 60-degree angle and arc actually of the triangle. Now what I'm going to get at here is within the lateral plane of the crystal we have the apex. This is where all planes converge and generates a condition of absolute polarization. You can't get any more intense than this. What we have intensifying here is right there. Follow the axis up to the apex, and we can identify the primes as it folds in to the apex. Now, as it folds in, it's also polarized adjacent. So we're making 3, we have a profile of 3, but we have the 6 primes working in opposites adjacently, assuming a kinetic type of a spin, if you want to call that, where the piezoelectricity, that's the pressure, if you apply pressure to the crystal, it upsets the equilibrium of inversion every time it's inverted. Now these inversions are at light speed, so it's very, you put a little bit of pressure on there, there's going to be electricity up the apex. This is a 2-dimensional, 3-dimensional converter. And what happens is that once that equilibrium is upset, it tries to reorient using its nucleus. Right at the radius is the nucleus. This is a new concept. This is what makes superstructure so unique. Because of the loss of equilibrium, it reorients. It tries to reorient, so it uses the electricity through beta decay, throwing out electrons. You see these lines here? This is the radius of a 180. This is the radius of a 180. It throws out an electron and a positron. That electron in this picture lands right here at the end of the plane, and the positron ends right there at the end of the plane. So what ultimately happens is that combined with the total polarization, the absolute polarization of the kinetic spin, and the beta decay of the particle being emitted, trying to restabilize the crystal, we have two. We have the kinetic spin, and we have the adjacent kinetic spin, and we have the external sheet right here, combined where now the electron might appear to be here, a little bit out because it uses the radius, so the electron might be a little bit further out from here. And if we do this at light speed, we see that we're creating the illusion of an electron orbit. This is what's been throwing everybody off the whole time because it's happening at light speed. If we could just still frame this like I've done in this model and show how that electron is being jetted out from the crystal's radius, we have a much better idea of predictability where that electron-positron configuration is going to appear. And combined with the spin, we can create the illusion of a orbital, an electron orbital. Now, getting that now through the stabilization, when the crystal becomes stabilized, that's when piezoelectricity dies down. That's the full working model of the superstructure, and I'm going to attempt to show now how reality is created from the polarized inverted end of each facet of the crystal. From this model, we have this just identifies the polarization and describes how the intense field is built. Let's get that centered. So the XY is on the Y and the X plane is opposing each other, both internally, externally, and where one line becomes polarized in two ways, where you have the XY, YX. That'll produce that. So to get, as I was saying before, to get this this one-dimensional actually material over to this side of the inversion where our reality exists. Let's get that focused in the middle there, guys. Okay, this is our reality, and we have the one-dimensional raw materials, as in, say, the protein version of amino acids. Say there's like 22 amino acids that need to be swung over there. So it uses the 137 prime, because the 137 prime, using the 60-degree leg of the equilateral triangle as a go-between, gets this material over there. The material is now used to form a reality of what our sensory input can use it for. In other words, we touch a table, we touch a hand. That sensory input tells us that it's wood, it's a hard object, and from that, the configuration of lines conform to the table, but being represented by prime numbers. Now, those prime numbers are the same prime numbers that are able to swing it back over to the one-dimensional side using the two-dimensional inversion table. And once it's swung back, once that 3D concept is formed by the linear material and swung back over using the primes, it is transformed into a star group. Now, how this is done is still, again, by the crystal. Now, we need a little model of the crystal here to show you. This is going to get intense. Now, you better put your seatbelt on. Everybody got their seatbelts fastened? Here's my crystal model. Okay, going back to this particular model of the crystal, we see the apex form. what we need is the inversion model of the 137. This is such a pretty model. This makes all the sense in the world of how they become primes and composites. Look at that, it just works like it was made to be. And so what we need is crystal. Alright, let's get closer to this. Okay, we don't have the model. We have the crystal model. I point the crystal to a mirror. Nose that crystal right into the mirror, so that we have a dimension, a mimic. The point becomes the 7th point of reference on the crystal. There's 6 outer planes plus the point equals 7. The 7 inverts in the mirror, forms onto a star group. Now, what's a star group that has 7 points? Well, let's see if we can come up with that. It's a Orion constellation, or Orion constellation, actually. And here it is. Guess what, guys? We just found. Here's where the crystal, quartz crystal, inverts, and you see those dotted lines? That generates a 2D, 3D. So that the 1D that's been passed over through the 2D is now 3D, is now three-dimensional, shoots blueprints a star group. That star group, the Orion constellation, becomes volume now. All that dark matter, the dark matter that we call, because we don't know what it is, becomes volume. That's two-dimensional space. What we have is a blackboard up there with the Orion constellation dotted out in 7 dots, 7 points of reference. That blackboard blueprints volume now, where there is 2 dimensions. And from that volume enters our memory. Every time we want to recall that memory, we reorganize those same prime numbers that referenced it in the first place and bring that reference into the 3rd dimension, from the 3rd dimension back to the 1 dimension through the crystal, and then invert it back over into the 3D reality. That's how the reality works. And now we're going to touch on how this superstructure becomes, in part, see if we can get this a little focused on here. This is an atom. These are 2 atoms. Okay, here's the covalent bond, the ionic bond. Let's not go covalent. Let's say this is the ionic bond. This is a strong bond. In the orbital depiction, we have the electrons exchanging places that lock the neutron and the positron and the neutron together, the nucleus of the atoms together to form the element. And this element, what I'm supposing, is that through the lateral point, through this 180-degree plane, they're locked into position by the prime numbers and the radioactive decay, producing the electrons that'll lock into that position. Now, this is the still frame of a light speed, something that's going on at light speed. This is just a snapshot of a still frame. Now, we can imagine how fast this is really going. There will be interinversions that will counter to hold that lock. Just like when the crystal blueprints and templates and blueprints a star group, that lock is only possible because of the precise moment in time and space of the Earth's rotation in the galaxy. Now that will be passed on to another crystal, which will pick up that lock. The first one loses the lock, the second one picks it up. And there's zillions of crystals, there's zillions of atoms, and this is how we're proposing that the superstructure plays out in the atom. Beta decay locking the electrons along the plane of a prime number plane. Now that's it for part A on this video, and it's a lot to absorb. So if there's any questions, you contact me on YouTube. Right. Stop recording. Stop.